the screen. Here we go.
We're good if you want to.
Hello?
Oh, hey. Is that how it normally
Yes, yeah, it's working, thank you.
Okay. All right. So we were going to continue on neural networks
Yes,
now.
everything is working.
My apologies for that.
Okay, great, thank you.
You all met for it earlier, so we'll just get into it.
Okay, cool. So the stuff that we've been talking about so far is really like the most basic type of neural network that you can come up with. And I've mentioned to a few people, it's pretty rare to see just a purely fully connected network like this used in practice. It's not unprecedented. I'm sure there's some good applications for it, but it's not really what people are talking about when they talk about neural networks being used in machine learning for the most part. So here is a crazy looking slide. This is a sort of overview of a lot of different types of neural networks. So what we've seen so far is this perceptron, or sometimes people call a multi-layer perceptron a feed-forward network. I've also heard that used to describe other kinds of networks. Basically, we have all of these different kinds of cells. Input, output, and hidden cell are what we've seen so far, right? So these are basically just multiplications with some weights and then an activation function. So obviously there's a whole lot more. Yeah?
Can you actually explain the difference between feed forward and the RBF, the radial basis network? Because they look exactly the same.
They do look exactly the same. I don't really remember what the difference is.
Okay.
So no, I cannot do that. I don't think it's important to understand everything that's going on in this. Well, I guess this deep feed forward is also kind of another example, maybe on a different scale, but the same type of network that we've seen so far. You can put a lot of different things into a neural network framework. So like a Markov chain, we've talked about before. I don't think of a Markov chain as a neural network, but you could. I mean, really anything that you can represent as some sort of network for doing computations, you could call a neural network. And I think that's probably literally anything. You could in some way coerce it into a neural network framework. And some of the software that we're going to be talking about is meant to basically do computations on graphs that look like this. So taking some input, running it through some graph, computing an output, and then doing the back propagation to figure out the derivatives. So it's actually going to be very convenient for us that so many of these different models, what else do we have in here that's, yeah, support vector machine. I guess most of the rest of these you would probably think of as neural networks, but like support vector machine is another one that I certainly would not call a neural network off the top of my head. But we're going to be able to implement any of these within one of those very flexible graph computation frameworks. So basically, if it's on this chart, or if you can draw it as a graph, you can implement it in TensorFlow or Theano or one of the other things that we'll talk about. So that's pretty cool. It means that we can do a lot more general computation than maybe it seems like when you first start thinking about what a neural network is. It seems like kind of a limited framework, and it's actually like a totally general framework. It just means that you sort of have to adjust how you think about this. So we're not going to get into too much detail about any of these. The names that you've probably heard before, maybe in the context of other lectures that we've already given, are maybe feed-forward network. Recurrent neural network is something that we'll talk about. And these convolutional, let's see, there's a whole bunch of different varieties. But anything with deep and convolutional is probably something that, yeah, like this guy here. So those are probably the two most common that you would hear about. All of these others are sort of variants on those, or maybe variants on the feed-forward network. So we're going to move on now, unless anyone has any more questions about this picture, which I probably can't answer, but good try. And this is, I have a link to place where this is from. Okay, so we're going to just do a little bit of discussion here of motivation. Hopefully people are already pretty convinced that these are powerful tools. There was this article that I saw a few weeks ago in the New York Times called The Great AI Awakening about all the cool neural network stuff that Google is doing. It's, I think do I have a slide? Did I already show the slide about machine learning at Google? I lost that somewhere. Anyway, Google is one of the leaders in all of this kind of AI machine learning stuff. I would recommend you read this article if you're curious about that field. There was also this paper in Nature recently talking about deep learning and how it's changing all this stuff in the sciences. And then yesterday, I saw this article from, I went to Stanford, so this deep learning algorithm does as well as dermatologists in identifying skin cancer, which is pretty cool. And it's the kind of thing that at this point probably shouldn't surprise you. Anything that consists of looking at some sort of structured input image and making a prediction about it is probably something that a neural network can do as well as you. Maybe that's a slight oversimplification, but I think provided enough training data, it's definitely true. Maybe the amount of training data is infeasible to actually gather, but I just thought this was a cool application. A little bit different from the recognizing faces and dogs and cats that is more commonly associated with this. Okay, so the only thing that I would caution is that although it is possible to come up with a neural network that solves these problems, this huge variety of problems in a lot of different ways, as we saw when we were playing around with the little neural network training example, it's also very easy to have a network that seems like it should work and seems like it should be able to represent the patterns that you care about, and have it just not work for mysterious reasons. So this guy's basically just talking about how even when you think you know what sort of deep learning approach you want to apply to a problem, it often ends up requiring a whole lot of manual fine-tuning of hyperparameters and things like that. Hyperparameters being things like the size of the model, the number of layers, the step size in the gradient descent, all those sort of things. So I guess I would say that, for this this cancer example, I would be quite curious to see if that actually works yet in real world settings. A lot of the time people can come up with a deep learning approach that solves a problem sort of for their training data. And it looks like it's going to do really well. It's sort of like people use deep learning for this driverless car technology stuff. It's kind of like teaching a car to drive on a closed track. Might just be an easier problem than the real world thing. So I guess I would just caution you in general that even though these methods have a whole lot of potential and can solve all sorts of problems, it's very easy to have them go awry or to trick yourself into thinking that you obviously already have the best solution when actually you've solved a much smaller bit of the problem than you realize. Okay, so moving on from that, the main thing that we're going to focus on in this section is this idea of convolutional neural networks. So this is sort of one piece of a deep learning network. Ashish is going to go more into the overall architecture of how the popular deep learning methods work, but we're right now just going to talk about sort of these individual building blocks that people use. So the idea of a convolutional network, they're usually used to look at 2D images. Okay, so think of this here as a 32 by 32 image. It has 3 channels, so red, green, and blue is usually the way that these are represented. So we have a 32 by 32 by 3 input block. And the idea is we want to learn to recognize patterns in the data that occur in little local regions. Okay, so when you look at an image, you sort of break it down into its different component parts, rather than looking at the whole thing as a single block. So the idea of convolutions is we're going to learn little miniature filters that will convolve over the image. Are people familiar with what convolutions are? Yeah, okay. I guess astronomy people probably would have seen this more often, but it's not at all a new idea. It's not peculiar to this idea of neural networks. It really just means that you're taking a certain little function. In this case, it's a little discrete k by k kernel. And you're convolving it with some input, so you're moving it around, taking the dot product at each point, and then summing the result over all the different channels. So that's all that it is. We're going to have a whole bunch of these little filters that we convolve over our input, and so the output is going to look like something roughly the same size as our input, because we moved the block all around the input. That can vary depending on how you move the filter around. But for now, we'll just say that it's the same size as the input image. But it's going to be much deeper. Originally, we only had 3 channels, right? Red, green, and blue. But now we have the output of filter 1, the output of filter 2, the output of filter 3, and so on. So depending on how many filters we choose to learn, we could only use 3 filters. That probably wouldn't be a very good choice, as we'll see. But more likely, we're going to have a very deep representation with the activations from a lot of different filters. Does that make sense to people? Great. Okay. Oh, and just to repeat this, the nice idea behind these convolutions is that we sort of preserve the local information in the image. So if we look at just the activation from a single filter, things that are highly activated here came from this part of the image. So in the neural network, in the feed-forward network, we sort of fed everything to everything else. We didn't have a spatially localized representation of our data. So here, the activations really correspond to the original point in the image. And that's sort of a nice property for learning things like shapes and edges and things like that. Is that clear to people? Great. Okay. So this is just another little picture here. Basically what's going to happen is if we keep doing convolutions over and over again, we're just going to be moving through these 3-dimensional blocks of different shapes. The reason that these shapes are decreasing is just because the way that the filter is moving in this case is it's actually skipping around a bit. So as we move it along, if we say moved by a stride of 3, so if we have a 5 by 5 filter and we move it 3 units at a time, then the output is going to be a fair bit smaller than the input. It kind of gets messy to keep track of the exact sizes of things, but for the most part, you don't have to. If you were going to write this in NumPy, you would have to, and it would be a nightmare. But for the most part, we're going to be using higher level libraries, and you just say, do a convolution, use this step size, and it'll keep track of all the borders and things like that. So this is sort of the basic thing that we're going to be doing, moving from one set of activations to another and just repeating. Okay, so here, someone sent a link to the Slack last time. That was smart. I'm going to do that. So if people want to load up this little page, I think it's quite a good demo for sort of understanding both what the. It's funny, I can't actually see the face from here because I'm too close. So for understanding both the data representation of images and for playing around with filters and activations and sort of getting some intuition for how convolutions work. So is everyone able to get to this page? Okay, so like before, I'll sort of drive over here, but if you guys want to mess around on your own thing, feel free to do that. So basically what we have here are white-black pixel intensities. So the 255s up here correspond to a totally white pixel, and the, I don't know, small numbers here, 20, correspond to a mostly black pixel. So in this case, we don't have the 3 channels that I mentioned before, we just have the 1 channel. If this was a color image, then we would have 3 separate channels. It's just a bit harder to visualize that way. So hopefully you can convince yourself that this image corresponds to this, to the matrix of pixel intensities over here. Okay, so in this case, we have a bunch of predetermined filters or kernels that we're going to convolve over the image. So this one's called the sharpen kernel, and it looks like this. It has a big positive value in the middle, little negative values, and then zeros. So what we're doing is we're taking this filter, we're starting up in the top left corner over here. We're taking the dot product of the numbers from that filter, 0, -1, 0, -1, 5, -1, 0, -1, 0, with the 9 pixel values right here, okay? So we have 206 times 0, 205 times -1, etc. We add all those up, which is why I'm calling it a dot product. It's element-wise product that we then sum. And then the total value there becomes the output value in our sort of filter activation space. So we can see here, this value is 69, which is relatively dark, and so that's going to be a relatively dark pixel over there. So that's really all there is to it as far as 2D convolutions. I would encourage you to like do this, walk the thing around. I know that this, when I was first learning about these, I sort of got the idea of convolutions at a high level, but I think it's actually quite helpful to like really think about what it means for a certain filter to be activated by a patch of your image. So I would say maybe take a couple minutes and walk the thing around and try to figure out like what kinds of patterns in the image are leading to different activations in the output, and then also change the type of filter around that you're using. Yeah?
Is there any way to preserve the boundary?
Yes. So what they're doing here is, if you notice, you can actually like kind of pull off to the side. Sorry, what do you mean by preserve the boundary?
So we lose the pixels on the edge, right?
I think that that's only true for this kernel. That's not true for okay. So I sort of glossed over this, but one of those sort of bookkeeping things in going from input size to output size is how you deal with the borders. If you just do what I was doing and you start here, what you're actually doing is you're going to have 2 fewer pixels going this way, right? Because we have a size 3 window. So it sort of starts at 3 for the rightmost pixel, 3, 4, 5, and then up to n. So you're going to have n minus 2 columns, and then similarly you're going to have n minus 2 rows. That's fine. There's nothing wrong with that. In practice, what a lot of people do is called zero padding. So they'll just add, oh no, so this isn't doing any padding. What you could have instead of these question marks is just zeros, right? So instead of losing pixels, you would just have a sort of, I don't know, a slightly different kind of value that you're taking on there. I think that's more common to do the zero padding, just because it's easier to like keep things the same shape as the image, Just makes it a bit easier to reason with, rather than having your images go from like 96 by 96 to 94 by 94 and so on. But yeah, there's different things like that. And then also, if you're not taking strides of size 1, if you're going like from here to here, then your image is actually going to get reduced by like a factor of 2. So it basically doesn't matter. I think it really just depends on.
Yeah, so there's only one thing. Sometimes if you want to keep the numbers even after you're doing max pooling, you may want to do a non-zero padding, so that during the next iteration it's again an even number rather than odd divided by 2. And you can provide that as a hyperparameter to most networks, so you can choose that dynamically also.
I think people also like to deal with data that has a size that's a power of 2, because a lot of the time that just happens to be a bit faster for the architecture of your computer. So a lot of weird little silly things like that might give you a bit better performance, but it's like in the small percent gain in efficiency. It's really not a big deal. So yeah, there's also this, I think this is another important thing to notice. We can also use this identity kernel, which basically just takes the middle pixel and returns it over. So we don't have to be doing any kind of crazy transformation. If it turns out that the feature, the image as it already is a good feature for a later layer, we can also just sort of pass it through. We can do all sorts of weird transformations just by doing different sorts of kernels. So have people gotten to play around with the different kernels at all? I don't know if this is useful, but I think it's fun. There's also this sort of more detailed image down here where you can see what the same kernels do. So this is what the original image looks like, and then we can do all sorts of things, identifying different sort of directional edges and sharpening, blurring, and all of these just correspond to some different little 3x3 weight metrics. I actually hadn't tried messing with any of the custom ones. It's kind of fun. Okay, so hopefully you are convinced that this idea of convolving a simple filter with your image can lead to sort of interesting changes in parameterization of your data. That's really all I'm trying to communicate right here. Let's close my slides again. Okay, that's the main idea there. And similarly, like I said that convolution isn't a new idea, using convolution of filters with your image, also not a new idea. This is how a lot of image processing techniques for a long time have operated. The filters that we saw in that example are filters that people came up with in order to achieve a certain purpose. They said, I think a filter that looks like this will be useful in identifying this. The key idea of these deep learning approaches is people aren't as good at coming up with choices of filters as we would like to believe. So what we're going to do instead is, we're basically going to start with completely random filters, and we're going to use gradient descent to iteratively improve our filters until they're starting to sort of pick out interesting structure in the data. That's, I guess, kind of a description of all deep learning in general. In this case, it applies to the little convolutional filters, but it's really the same as the weights in our perceptron or anything else like that. So we can see here the filters that, this is from a network called AlexNet, which was one of the first deep learning networks to make one of those big dips in classification error, probably 2012 or something. And it's kind of interesting because a lot of these filters actually do look quite a bit like filters that humans came up with, sort of mathematically derived filters that were used for different image processing tasks. But no one ever prescribed this kind of structure. No one ever said, like, take this filter, it's pretty good, but make sure you also have like the 90-degree rotated version, because that might also be good. These are just completely arbitrary filters that were learned by the network. So if you've ever heard people talking about deep learning as this crazy like runaway, like it's teaching itself to learn and Skynet and all this stuff, that's pretty far off, but you can sort of see where like tech journalists get off using that kind of language, because the idea of the machine just deciding how to transform the data is sort of spooky, I guess. And that's basically what's happening here, yeah.
So how does the algorithm evaluate what's a good filter or not?
Well, that's the thing, is it doesn't really need to worry about that per se. What it's doing is, we have a computational graph. We have inputs, and we have predicted probabilities from a softmax function, just like before. So we can compute our classification loss using the exact same loss function that we were using in that example, except that now, when we do that backpropagation to compute the gradient, there's a bazillion different parameters that we need to update. But it's the same procedure. We just walk through that graph. At each step, we apply the chain rule. We take the derivative from the previous step, compute the derivative of the current function, and then multiply them together. So what we're going to get out of that is a gradient step to take for every single parameter in our network. Some of those parameters are going to be these filters. So these look like, I don't know, 9x9 filters. So in this case, each one of these is going to have an 81 parameter gradient descent update that's going to be performed for every single one. So it's really sort of a it really is sort of an automatic process, and it just sort of happens to be the case that the filters that do the best for these image classification tasks do often resemble filters that humans come up with, but not always. Some of them are just weird and crazy. Like, I don't know what's going on here, but apparently that's useful. Yeah.
And what do the colors correspond to?
Yeah, I don't actually know. Ashit, have you seen this picture? Do you know why some of them are black and white, some of them are RGB?
I think those are two different things, aren't those? So the different filters that you mentioned, right? The different layers that come about. So some of them are individual colors, and if they are individual colors, those will just come as grayscale. Whereas the others are using all three.
Oh, okay.
Those multiple ones.
Wait, don't you use the same filter for all three channels though?
Not necessarily.
No, that's okay. Okay, so yeah, I guess those are just filters. In this case, these are filters that are being applied to all of the colors, and here we're sort of learning color-specific ones. So this one is helpful for green for whatever reason. Who knows why? Yeah.
Do you have a stack of like the three filters? Do people make n-dimensional filters or n-dimensional filters that you can sort of?
I think what is typically done, and it could vary quite a bit, is you learn filters that you apply to each dimension separately, and then you combine them. There's actually, I'll maybe demo it later. There's a cool little JavaScript visualization of that I wanted to show, but I didn't have time. Where you see them apply the same filter to the R, G, and B channels, and then they sum them up. That's not the only way you can do it. Like she said, you can also learn them for specific colors. You can also, so what I've been talking about is using the same filter across the whole image. You don't actually have to do that. You can learn different filters for different parts of the image. You can do whatever you want. It's really the Wild West. It just so happens that it's a good, like, efficient use of your number of parameters to learn things that you apply everywhere. But there's no hard fast rules about this. These are all just sort of like aggregate conventional wisdom assembled over 20 to 60 years, depending on how you count, of trying to use convolutional networks to do stuff. So it's all, very, very little of it is like provably the best thing you could do. It's just some guy did it and it worked one time. Okay, so another thing that maybe you've heard mention of is this idea of pooling. And this is another thing that's really just a practical consideration. So, like I've said before, since we have these filters and we apply them everywhere, you can get a lot of mileage out of a single good filter, because it's going to give you interesting information out of every single part of your image. But the problem is, if you think again about what actually I should have had a slide like this. If you think again about the size of this output, if you have a lot of filters, this thing can be pretty massive. So this is a 32 by 32 image. If you have a 1024 by 768 image, and you have 256 filters that you apply, then the size of this output is going to be 1024 by 768 by, what did I say, 256? Yeah, and that's a lot. That's a whole lot of parameters to keep track of and a whole lot of numbers to calculate. And then if you want to feed those things into a next layer, you're going to need a weight for every single one of those. So the output size being really big increases the number of parameters you need in your next layer to accommodate that. Does that make sense to people? It's sort of a subtle idea, but basically the idea is if you have a really big output like this, it's probably not ideal, and it's going to be very computationally expensive to deal with. So one solution that people have come up with, by no means the only solution, is to do this thing called pooling. Basically, we're just spatially downsampling the activation map. Not the original image. We're keeping the original image, feeding it in, taking the full convolution, and then throwing away some of the information that we think is not important. So a very, very common thing to do is 2x2 max pooling. That's probably the most common kind of pooling operation. You can do all sorts of variations, but basically it just means if from this depth slice right here, so this is the output of one filter, if it looks like this, then we're going to look at all of the 2x2 chunks and just take the maximum value from each one. The idea being that we want to throw away some information, and you could, actually, I don't really, Ashish, do you know why people prefer max pooling to mean pooling?
So many times they want to simply highlight something, one of those, and then max gives you from that. But people do mean as well.
Yeah. I guess basically the idea is that we're training neurons to like recognize things, and if you have a high value, that means something was recognized.
Yeah, the
And
means
so,
smooth things out rather than.
right, rather than it sort of goes back to this idea of like introducing nonlinearities. I guess the maximum is a nonlinear function. So that's basically what we're doing here. This thing, we've reduced its size by a factor of 4, which is pretty considerable. If we have a bigger image, maybe we would do 3x3 max pooling or 4x4. Again, this is just another hyperparameter, and if you're designing a network from scratch, it's something you need to think a lot about. If you're going to use somebody else's network and try to apply it to your problem, then they've done all the hard work for you, and this is probably not one of the things that you need to worry about. But it's important, I think, to understand like roughly what's going on. This is the wrong picture, it seems. But yeah, basically, now that we've talked about convolutional layers and pooling layers, you pretty much understand what the building blocks of a convolutional neural network are. And that's pretty cool. So we basically just repeat this structure over and over again. When you talk about deep neural networks, that can mean, I don't know, 5 layers, 200 layers, really depends a lot on the application and the type of data. But we're usually just going to be repeating layers, sort of roughly following a convolutional pooling, convolutional pooling, convolutional pooling, maybe multiple convolutions next to each other, just depends. And then at the end, it's common to have a little fully connected network at the very end that sort of takes the features learned by the convolutional network part and builds a nonlinear classifier to turn those into probabilities. Does that make sense? So it's almost like we have a really simple network, like the perceptron that we trained in NumPy, but the thing that we're feeding as inputs are very, very complicated filter activations from this deep neural network. But if you sort of view them separately, it's like training a simple nonlinear neural network classifier on crazy features that the network has learned to extract from the data. So here's an example. Ashish is going to talk more about architectures, but just so that you can see kind of what I'm talking about, this is what VGGNet looks like, which is just one of the successful architectures from the past few years. And it, like I said, it's input, convolution, convolution pool, convolution, convolution pool, convolution, 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 just repeated a bunch of times. How they arrived at this particular sequence of layers, I have literally no idea, but I assume it was something along the lines of, hey, what if we put another convolutional layer in there? Okay, sure. And then they try it, and it increases their classification accuracy by 0.2%. And they're like, okay, great, let's keep it. That's really what a lot of it comes down to, is kind of guessing and checking. Okay, any more questions about convolutional networks before I move on to the next bit? Everyone's great on convolutional networks. Okay, awesome. So mostly so far, I've just been talking about image data, and that's usually what 2D convolutional networks are used for. But you might have a lot of other kinds of data that you want to deal with. So one common problem is looking at sequence data, or maybe you want to take a single data and generate a sequence out of that. So these are sort of, I guess, obviously the different types of mappings of inputs to outputs. The image classification problem is this right here. We have an image, we extract some features, and then we say, what is it? Is it a cat or a dog? But like I mentioned before, there are a lot of other uses of these neural network techniques. So things like language modeling and text analysis, those deal with word sequences. And sometimes if, actually like Google Translate is a good example. The main method that Google Translate uses now is a crazy complicated neural network. And what it's doing is it's reading the individual things, it's passing those into different neural network signals, taking the activations, and what you get out is a sequence of activations. So the convolutional network architecture isn't ideally suited to dealing with sequences of inputs. It really just takes one thing and gives you one thing out. There are exceptions to that, but that's generally true. So the question is, if we have sequence data like this, or if we want to output sequence data, what's a good way of dealing with that? So the main way that people deal with this is called recurrent neural networks. I think somebody mentioned it briefly at some point. But it's actually, I think, pretty simple, at least at a high level. The idea is we have this, I would look at this side of the image first and then convince yourself that it's equivalent to this. So we have a bunch of inputs, and these could be numbers or they could be vectors or whatever. We take each input in our sequence, we pass it as an input to some sort of neural network, and that neural network outputs a new value, a prediction for that input. And then we basically just keep doing that over and over again. So it's almost like just looping over your inputs in a for loop. The difference is that this cell A contains some state, internal cell state, that updates each time it sees an input. So it's not the same as applying just the same function to every input. It's sort of gathering information as you go along. So you could think of this as, like for translation, say, this is a bit of an oversimplification, but if you were trying to translate something, you might have you might be gathering some context as you go along that would inform your translation decisions for future words. Does that make sense? If there's some ambiguity here about how you should translate this, maybe the past sort of information that you've gathered could help you to make a better decision. For something like sentiment analysis for text, all you really care about is making one final prediction at the end. So what you could do is you can take all of the inputs in a sequence, feed each one to your recurrent cell, and throw all of these away. You don't actually necessarily care about taking a sequence output. So like in the thing I showed before, you can have one to many, or many to one, or many to many. In this case, it's drawn as many to many, but it doesn't necessarily have to be like that. You could only have one input, or you could only use one output. Either of those is fine. So this is just sort of a general framework for processing a sequence of data, aggregating a bunch of information about it over time, and outputting either one prediction per time step or one class label at the end. Any questions about this basic schematic here? And it's important to remember that this thing is also updating itself each time as we go along. That's sort of the key fact about recurrent neural networks, is that this thing is learning as it processes the sequence. Okay, great. Yeah?
Is it updating the neural network, or it's also by passing some result?
Yeah, so it's sort of a subtle thing. What happens is we train all the weights. So this thing has some internal weights, and then it has like a state vector. So the weights are fixed, and the state changes. So there's like,
So it's
you
not
can
like
see if I write on this. The whole formula for a recurrent neural network really looks something like, we have some state 0. When we see a new data point, we say, take this input and update my state. And this is parameterized by some kind of state update weights. And then output ht+1, which is some different function of, sorry, I guess this should be the input and the old state. And then this is a function of the input and the new state. These might be fun, and then this is parameterized by a different set of weights. So it is kind of a subtle thing. Part of the network is being updated as you go along, but these weights are fixed. The process of training is learning the functions that go like this and like this. But then those are fixed, and you just sort of roll through this procedure. Does that make sense? It's kind of subtle, but hopefully it isn't too confusing. Okay, no one looks confused, so. Okay, so we're not going to spend too much time on recurrent networks. I'm sure that there are plenty of astronomy applications. I would expect that convolutional networks would just come up a lot more, since you deal a lot with image data. But for time series type information, these are certainly a good approach. The only other thing that I'll mention is that in practice, a very simple neural network system, like I mentioned, where the state just updates itself each time, is not very good at handling long-term dependencies, because like I wrote there, you recompute the state each time, and you're sort of feeding in a whole new data point, and it turns out that it's difficult to teach the network to preserve information from a long time ago, even if that would be helpful. There's no reason that those networks can't do that. They can learn arbitrary nonlinear functions of their inputs. So it could be the case that they could learn, just keep this part of my state as like a long-term memory of something. But it just turns out that in training, it doesn't really work that way. They forget things from the past very quickly. And so if you have something like a paragraph from a news article that you're trying to analyze, and you say, Donald Trump did some horrible thing, and then later on in the paragraph, it mentions something about Donald Trump, but it doesn't re-mention what the horrible thing was. Maybe the interpretation of what the later thing Trump did is determined by that first sentence. Does that kind of make sense? If there's any kind of long-term dependence in your information, you're likely going to lose it with this standard recurrent neural network system. So I'm not going to go into the details, but there are variations on this basic recurrent cell that sort of introduce a few more tuning parameters. And basically what this does, these are called gates. What we do is we sort of learn to be able to decide not to update the state. Does that make sense? So if we think that part of the state should just remain the way it is, then this gate will close. They're basically activation functions that get applied to the input. So in different complicated ways, we'll decide, you know what, I'm gonna just skip part of this round of state updates. And similarly, when you're constructing the output, there are sort of rules about whether you should take more of the state to determine your output or more of the current input. I know that's a very hand-wavy explanation, but it's actually super complicated, in my opinion at least. It's not as simple as the convolutional filter idea. The sort of canonical example of this is called an LSTM, long short-term memory cell. GRUs are another slightly more modern way of doing this. It's basically just a different configuration here, so we pass the information around in a different way. But basically all you need to know is if you think there might be any kind of long-term autocorrelation in your data or interaction between things that are temporally separated, then you probably want to use one of these and not a standard recurrent neural network. I actually don't know of hardly any applications of recurrent networks that aren't LSTMs. So for your purposes, maybe this is the main implementation of LSTMs. There's this really good blog post which goes into crazy detail and tells you exactly what all of these gates do. So if you are very interested in this, I would definitely recommend checking it out, but we're not going to do that think you've already seen something from this blog post in someone else's talk. But these are examples. So we saw in the TensorFlow playground thing, the way that different neurons learn to activate for different parts of the input space. The same thing is happening here for different recurrent cells for different parts of a text input. I think this is really, really crazy. All that they did was try to train a model to, I think, predict the next word in a sequence, or maybe given a context, predict the missing word. So it's a totally unsupervised thing. They're not trying to do any kind of classification or anything like that. But nevertheless, this really wide variety of cells sort of comes into play. So these cells up here are, I guess blue is probably positive and red is negative. So these are firing when you're near the beginning of a line. These are firing when you're inside quotes. So when you saw the example the other day of that auto-generated C code, I actually might, if I have a couple minutes, I might go to that blog post and show you some more examples. It really needs to keep track of a lot of stuff to make something that looks like plausible C code. It has to know about parentheses, it has to know about braces. I don't know if the indentation is something it's doing, or if they're doing that after the fact. But it really does have to learn quite a few complicated things. And so this is something that fires, oh no, I guess red is active right now. No, these seem to sort of,
If there's some sound there,
what's that?
I think there's some sound, because the next one's obviously red is on.
Yeah.
What is the gradient in the top paragraph imply?
It's basically, it's saying how close am I to the beginning of the line. Yeah. I mean, like, this is all very, very post hoc reasoning. No one designed these to do anything like that, but you can just look at where they activate and see, okay, obviously what this is doing is it's learning to activate inside of an if statement. That seems pretty unambiguous. These are probably very like cherry-picked examples. In fact, I think there's one here that's just weird and crazy. And that's not really that surprising. The thing that's more surprising is that these do have such nice structure. Because again, all that we're trying to do is minimize some very specific loss function. We as humans would prefer things that look like this and follow a certain structure, but it's not necessarily obvious that that's the optimal way to solve that task. So it's pretty cool that that happens. Maybe I'll show you just a couple of other examples from here. So, oh yeah, so this is automatically generated Shakespeare text. And it doesn't make sense, but like, maybe if you aren't really paying attention and you just sort of glance at it, it definitely looks like, you know, if you squint, it could be real text.
Wait, was that naturally generated philosophy?
I'm not sure what this was trained. Oh, just all, I guess, a bunch of Wikipedia. This is actually my favorite. The randomly generated algebraic geometry. So this, yeah, this is an automatically generated. To me, at least, this could easily be a real archive paper. So it's really, really good at learning these very subtle things, right? Like that these sort of symbols go together, and if you have this kind of symbol, you need to have another symbol come somewhere after it. A lot of this stuff involves very strong long-term dependencies, like I was talking about. So if we weren't using, these are all LSTMs. If we weren't using an LSTM, we would really just get like small groups of characters that could belong together, like words maybe, but the like sentences wouldn't have any kind of coherent structure. They would really just be like words. So I think this is pretty wild. And then this was the fake Linux source code. Like I would believe that this is real Linux source code, except this probably isn't a great but like for the most part, it really looks, I don't know, if you're not an expert in C at least, to me it seems.
Yeah.
Have neural nets made code yet that can like compile and actually do something?
Yes. I don't know about do something, but people have used these to write programs. Yeah, because if you think about it, the loss function here is looking vaguely like the text that was input. But if your loss function was something more like, adhering to the rules of a programming language, then it would certainly learn to generate code that at least runs. I guarantee you there are people at Google who are working on some sort of weird, nefarious thing like that. So anyway, there's a bunch more examples here. This is where I got those activation maps. Yeah, I think this is really cool, but there's a lot here. So if you're curious about this recurrent neural network stuff, then I would definitely check that out. Okay, so we're almost out of time, but that's okay because I'm almost out of slides. The only other thing I'm going to mention is I've sort of alluded a lot to these frameworks that let you do deep learning stuff. Basically, what they all have in common is if you can represent your computation as a graph, which for neural network stuff you always can, then any of these will give you nice tools for being able to handle that. So probably the most popular right now is TensorFlow, which is from Google, but there are advantages to all of these others as well. Cafe is probably on the way out. That was very popular for a while. You could download a lot of pre-trained networks, but I think that for the most part, you're probably going to be fine sticking with Theano and TensorFlow. The exercise that we're going to do is actually going to be using Keras. It's a bit hard to write raw TensorFlow code, in my opinion. There's a lot of stuff to keep track of. And Keras is this very, very nice, slick interface, kind of scikit-learn-esque, that lets you just construct a model with some pretty simple expressions, fit it to data with a .fit method, make predictions with a .predict method. Very, very straightforward. It was actually quite a challenge to come up with a non-trivial exercise for you guys in Keras, because it's so easy that I had to sort of deliberately obfuscate it a bit. It's just very, very, very simple to construct these networks. So here's a graph of popularity by a couple different metrics. This is from Francois Cholet, the developer of Keras. But if you care about GitHub stars, which you probably should, TensorFlow is by far the most popular, and Cafe sort of had a big head start, but Keras is very rapidly gaining on it. So I think that this is pretty good motivation for the idea that TensorFlow, Theano, and Keras are probably, if you're a Python person, the main ones to worry about. I've also heard that MXNet is the fastest, but that's, unless you are really interested in cutting edge performance, it's probably worth it to just stick to something that has better documentation, more Stack Overflow questions, and I think that at this point, TensorFlow and Keras are probably the easiest to get into. So that's most of what I have now. Yeah. So we'll finish up. The only other thing that I'll mention is that the main reason that those frameworks are so good computationally is they're able to leverage GPUs a lot. Presumably no one in here has a beefy GPU in their laptop, but for research, it's now very, very easy to get an EC2 instance on Amazon with a crazy GPU or with 8 crazy GPUs. And we're able to take advantage of the sort of parallel nature of the training process on GPUs. The reason it's parallel is the training algorithm looks like take all of the data, compute the gradient of the loss function with respect to each sample in the input, add them all up, and then do an update. So all of those gradients as long as the model parameters haven't changed yet, all of those gradients can be computed completely in parallel, and they're pretty simple operations. So basically, that's exactly what GPUs are designed to do, is lots and lots and lots of simple operations in parallel. So these frameworks are able to distribute your backpropagation steps between different cores of a GPU, and it'll really speed your computations up quite a bit. If you are just dealing with toy data sets, like we're going to be in this exercise, you don't need a GPU, but I would say having one nice GPU is probably 50 times faster than doing it on your laptop, and then if you have a whole cluster of GPUs, it just goes up from there. So when Google's doing stuff, they have hundreds of millions of data points, and they need hundreds of GPUs, or actually they have their own sort of GPU variant called a TPU, tensor processing unit. That's just their custom hardware. But basically that's the fundamental thing that we need to do to train a network, is take bits of our data. Usually the whole data set's too big to fit in memory if we have like a massive thing, or the whole data set plus all of the gradient computations. So we'll take batches of the data as big as we can fit in our GPU, compute the gradient for each one, and then take a gradient descent step for each batch of data. That's the whole of optimization as far as you're concerned. And that's just sort of the overall reason why GPUs are so useful. Okay, so that's all I have now. So it's time to do another exercise, I guess. Should we head back to the...
All right, let's
oh, yeah.
thank you first. And I'll ask, are there any questions?
That's also a good question. Any questions? No. Ashish is going to be talking later about some of the more nitty-gritty stuff as far as deep learning is concerned. This is really just about the sort of building blocks, and then putting them all together can be a very complicated task. No questions? Okay, great.